Hello everyone, my name is Bhagyadeep Kalal from LJ Institute of Engineering and Technology. Today I discussed air refrigeration system part 1, lecture number 3. Today topic is a reverse carnot cycle, second one is a Bell-Coleman cycle, and third one is the advantages and disadvantages of Bell-Coleman cycle, and fourth one is a actual Bell-Coleman cycle. Before the starting of reverse carnot, we explain first air refrigeration system. In air refrigeration system, air as a working fluid or its work refrigerant as a refrigerant work in a cycle. Okay, because nowadays this system of this cycle is absolute. It is not used nowadays because low COP and high cost of maintenance or equipment. That's why it is not used nowadays. Okay. First of all, we discussed reverse carnot cycle because reverse carnot cycle have a maximum efficiency. That's why we compare with this cycle and study next cycle. Okay. First, reverse carnot cycle does reverse the direction of heat and work interaction. Heat and work interaction. A refrigerator or heat pump that operates on the reverse carnot cycle is called a carnot refrigerator or carnot heat pump, which is already studied in thermodynamics. The reverse carnot cycle is the most efficient refrigeration cycle operating between two specified temperature level, that is a source and sink, which is already studied in thermodynamics. That temperature is almost constant. If you take into temperature like 50 degree and 50 degree centigrade, that is high temperature, and lower temperature, that is a 20-degree temperature, this is always constant. Okay. Source and work as a source temperature and sink temperature. The most things in reverse carnot that it sets the highest theoretical COP, highest theoretical COP, highest theoretical COP. Okay. Now I discussed all the process in the reverse carnot cycle. All the process in the reverse carnot cycle. Reverse carnot cycle. I shown here a layout diagram of reverse carnot. Here, four components are used. One is a evaporator, that is a isothermal process. Evaporator in which isothermal process occurs. Second one is a compressor, that is a isentropic compression process. Third one is a condenser, that is a isothermal heat rejection process. Isothermal heat rejection process. And last one is turbine. In turbine, isentropic expansion process. Okay, one by one we explain. 1 to 2 is the evaporator refrigerant absorb. Here refrigerant as a air absorb heat isothermally from a low temperature source at TL. There is a temperature TL in the amount of QL. QL is the amount of heat. TL is the low temperature. Okay. Here our desire is a cold medium, which we required cold place here. So evaporator absorb the heat from cold place. Next, 2 to 3, refrigerant compressed to state 3. To state 3, temperature rises to pH. Here temperature is increases. Entropy is a constant. Entropy is a constant because it is an isentropic compression process, and pressure also increases. Pressure increases, temperature increases, and entropy constant. Next, 3 to 4 process, that is the heat rejected at constant temperature. Refrigerant reject heat to high temperature at TH. TH is the temperature in the amount of QH, that is the amount of heat QH. Refrigerant changes from saturated vapor state to saturated liquid state in the condenser. But if air as a refrigerant used here, it cannot change its phase. Okay. 4 to 1, the refrigerant expands adiabatically to state 1. To state 1, refrigerant expand adiabatically. Adiabatically means isentropic process, because in which entropy is a constant, temperature decreases and pressure is also decreases because here expansion process occurs. Now, this low temperature refrigerant drawn into evaporator so that this cycle is continuously one from 1 to 2, 3, 4, and again 1. Okay, here I draw a TS diagram with respect to layout diagram, evaporator, compressor, condenser, and turbine. Cold air, this is your desired place, TL temperature. At low temperature, heat is absorbed by evaporator, that is a QL 1 to 2 process, that is a evaporator 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 process. Next, 2 to 3, that is the entropy constant, that is S2 equals to S3. S2 equals to S3, entropy is a constant, entropy equals constant, S2 equals to S3, but temperature increases, temperature increases, temperature increases, pressure is also increases. Okay. Next, 3 to 4. 3 to 4 is a condenser process. Here, heat is rejected to warm medium, that is a TH, where temperature is a TH. Temperature is a TH. Okay. Next, turbine. Turbine here, isentropic compression process, isentropic expansion process, where temperature where temperature decreases and pressure is also decreases, pressure is also decreases. Here, so 1 2 2 3 4 and 1, the TS diagram is the temperature. T3 equals to T4, T3 equals to T4, T2 equals to T1, that is a low temperature, and heat is absorbed at low temperature, heat is rejected at high temperature, that is corresponding temperature is a TH. Next, reverse carnot cycle, PV diagram and TS diagram. 2 to 3 adiabatic compression, 2 to 3. Here 2 to 3 adiabatic compression of the working fluid by using external work. The temperature of the fluid rises from T2 to T3, and 3 to 4 is a isothermal compression of the working fluid, during which heat is rejected at constant high temperature, let me say T1. 4 to 1 adiabatic expansion of the working fluid. The temperature of the working fluid falls from T4 to T1, T4 to T1, T4 to T1. Okay. And 1 to 2 isothermal expansion, 1 to 2 isothermal expansion of air, where heat is absorbed at low temperature, we can say T2, from space being cooled. Uh, Here some changes. This is 1, this is 1, this is 2, and this one is a, okay. In diagram some changes. This is 3, this is 1, this is 1, and this is, okay. 2 to 3 adiabatic compression. 2 to 3. This is adiabatic compression. Let's see, this is adiabatic compression. Here, pressure increases, pressure is increases, or temperature is also increases. In TS diagram, temperature increases, and entropy constant. In TS diagram, S1 is equals to S2. There's here also changes. This is 3, 2, 1, and this is S1 is equals to, here S2 is equals to S, okay, S2 equals to S3, 4 equals to S1. Okay. And 3 to 4 isothermal compression, 3 to 4 isothermal compression, 3 to 4 isothermal compression, isothermal compression 3 to 4, that is isothermal compression 3 to 4, 3 to 4 isothermal compression, where pressure is increases, temperature is also increases, but heat is rejected to the surrounding. 4 to 1, 4 to 1 is a adiabatic expansion process where pressure decreases, temperature decreases, but entropy is constant. See in the TS diagram, 4 to 1, S4 equals to S1, entropy constant, and 4 to 1 to 4, 1 to 4 is the isothermal expansion process, isothermal expansion process, isothermal expansion process 4 to 1, 4 to 1, where heat is absorbed, heat is absorbed, that is Q2, okay, but temperature is constant, that's why S T1 is equals to T4, T1 is equals to T4. Okay. Now COP of refrigerator. Now COP of refrigerator. Now COP of refrigerator. COP of refrigerator. Heat absorbed Q2, that is T2 ds. How to write this T2 ds? With the help of entropy. Entropy is equals to Q by T. That's why we write here Q2 is equals to T2 into ds. It rejected Q1 at T1 into ds, T1 into ds. Net heat. Net heat is equals to work input is equals to heat rejected minus heat absorbed. Heat, how net heat is equals to work input? Because according to first law, the cyclic process, so cyclic integration of net heat is equals to cyclic integration of net work. That's why we write net heat is equals to work input. So we get W is equals to Q1 minus Q2, T1 ds minus T2 ds is equals to T1 minus T2 ds. And we know that the COP of refrigerator already in lecture 1, COP of refrigerator, COP of refrigerator, that is a cooling effect divided by work, divided by cooling effect, that is your desired work input, that is a W, that is a Q divided by W. Desired effect is where we obtain, that is a Q2 at evaporator, and network, that is a Q1 minus, that is a Q1 minus Q2, that is a Q1 minus Q2. Okay, is equals to Q2 written as T2 ds, T2 ds. Okay, Q1 minus Q2 is written as T1 minus T2 into ds, T1 minus T2 into ds. Okay, so finally ds or ds cancel, we obtain T2 divided by T1 minus T2. So COP is equals to T2 divided by T1 minus T2. T1 minus T2. Again, another method how to find out the COP. Another method also, heat absorbed, that is the heat absorbed Q2, and work supplied, heat rejected minus heat absorbed. Put all the formulas here and we get T2 divided by T1 minus T1. T2 is what? Low temperature, T1 is high. Final conclusion of COP of reverse carnot is that it does not depend on any refrigerant which used in reverse carnot. Basically, COP of refrigerator, reverse carnot refrigerator, depends on the two temperatures, specified temperature limits, that is the higher temperature or lower temperature. Okay. And it gives the maximum COP. Gives maximum COP. Gives maximum. Okay. Next, limitation. The main question, limitation reverse carnot cycle. The main understanding is that what is the limitation of reverse carnot cycle? Why it is not practically possible? Okay. Practically, the reverse carnot cycle cannot be used for refrigeration process purpose, as the adiabatic process required very high speed operation, where the isothermal process requires very low speed operation. Both processes cannot operate simultaneously, because isothermal process is a quasi-static process, where adiabatic process very fast, very high speed process. That's why both process simultaneously cannot be possible. Reverse Carnot, that's why reverse Carnot cycle is not practicably or physically possible. Second thing, large volume of pressure handling. So uh, volume of air and pressure is a large, that's why it cannot handle. So if it handle, the size of refrigerator becomes bulky and heavy. Bulky and okay. Next cycle, the main important cycle, that is the Bell-Coleman cycle. Bell-Coleman cycle. Because Carnot cycle is not practically possible, so we study next Bell-Coleman cycle. Only changes is in Bell-Coleman to we use two constant temperature process in reverse Carnot cycle. Now we use two constant pressure process in Bell-Coleman cycle. Only two process are changes in Bell-Coleman cycle. The Bell-Coleman cycle, also called as the Joule or reverse Brayton cycle, also called Joule or reverse Brayton cycle in a refrigeration. The working fluid is a gas that is compressed and expanded isentropically. Isentropic, but does not change its phase. Air is most often this working fluid, most oftenly used as a working fluid. This cycle may be thought of as a modification of reverse Carnot cycle. This cycle may be modification of reverse Carnot cycle as the two isothermal process of Carnot cycle are replaced by two isobaric heat transfer process. Okay, here I show the diagram of the Bell-Coleman cycle. Here four devices are used, four components are used. First, there is a heat exchanger. Second is a turbine, a heat exchanger, second heat exchanger, and last compressor. Four devices: heat exchanger, compressor, turbine. Heat exchanger where heat absorbed from cold reservoir or cold place where you want to put is cold. Heat is absorbed, that is heat exchange. We can say here is like evaporator, but it is not evaporator. It's a one type of heat exchanger. Okay. Next compressor, and next heat exchanger second like cooler, and heat exchanger one is like a refrigerator, and heat exchanger here is a cooler. Then turbine. Four components are joined each other. Now, in four components, what happens? First, that is the refrigerator, heat exchanger one. It absorbs heat from cold place at low temperature and drawn into compressor. Drawn into compressor. In compressor, in compressor, the air is compressed. The air is compressed isentropically. That means entropy is a constant, pressure increases and temperature is, and then 2 to 3, that is a 2 to 3 is a cooler or heat exchanger where air high pressure air is drawn into a cooler where heat is rejected to reservoir, that is a too hot. Heat is rejected to hot reservoir outside or atmosphere at constant pressure. At constant pressure. Next, this air is next drawn into a turbine where isentropic expansion process occurs. Isentropic expansion process occurs. 3 to 4 isentropic expansion process occurs, in which entropy is a constant, pressure decreases and temperature is also decreases in the turbine. Pressure decreases, temperature decreases in the turbine. So in turbine we get some work. We get some work. Sometimes it can be neglected, but we obtain some work. This work is transferred to the compressor. Compressor also take a heat from mechanical energy, that is from outside or motor, and also from a turbine. Okay. Next, PV and TS diagram PV and TS diagram of Bell coleman. 1 to 2 isentropic PV diagram. We explain first PV diagram. 1 to 2 is a isentropic expansion process. 1 to 2 isentropic expansion process. Pressure increases from P1 to P2. Next, 2 to 3. 2 to 3. Constant pressure, heat rejected. Constant pressure, heat rejected. Constant pressure, heat rejected. Pressure is constant. Pressure is constant. 3 to 4. 3 to 4. Isentropic expansion. Isentropic expansion. 3 to 4. Isentropic expansion where pressure decreases from P3 to P4. P3 to P4. Specific volume also increases. Specific volume increases. Okay. And 4 to 1. 4 to 1 process. 4 to 1 process. 4 to 1 process. Heat is absorbed. Heat is absorbed from cold place. Here the component is used here, the refrigerator or heat exchanger. Here cooler is used. Here cooler is used. But for 2 to 3 and 4 to 1, 2 to 3 and 4 to 1, both processes are constant temperature or constant pressure. Constant pressure. Okay. So expand here now. Expand TS diagram. TS diagram. TS diagram. Okay. TS diagram. 1 to 2 is isentropic compression, entropy constant, temperature increases, that's why there is a straight line. There is a straight line. 2 to 3, the pressure, constant pressure, or heat is rejected, that's why temperature decreases, okay. And 3 to 4, isentropic expansion, temperature decreases, isentropic expansion, temperature decreases. Next 4 to 1. 4 to 1 heat absorb. That's why temperature of the cycle, temperature of the system increases. Okay. Here heat is absorbed, and here heat is rejected. Heat is rejected. But 2 to 3 and 4 to 1 is a constant pressure. P is a constant. So explanation are here. First one to do is isentropic compression. The air is drawn from the refrigerator to air compressor cylinder where it compressed isentropically. No heat transfer by the air during compression. The volume decreases while the pressure and temperature increases. Similar like 2 to 3 constant pressure cooling process. The warm compressed air passed through the cooler where it cooled it down at constant pressure. The heat rejected per kg air during this process is equal to Q2 to 3. How much amount of heat rejected per kg? That is Cp T2 minus T3. Cp T2 minus T3 is like mc delta T. We know that in thermodynamics Q is equals to mc delta T. That's why Q2 to 3 written as Cp m is equals to 1 because of calculating per kg mass. Next 3 to 4 process. Isentropic expansion process. No heat transfer takes place. Isentropic expansion. The air is expanded isentropically in expander, and during expansion the volume increases. Main thing is that the volume increases, pressure P3 reduces, P3 to T4, temperature also fall during the expansion from T3 to T3 to. Next, constant pressure heat transfer from refrigerator to air. 4 to 1, the temperature increases from T4 to T1, volume increases to V1 due to heat transfer. Now, heat absorbed by air per kg during this process is equal to Q4 to 1, that is Cp T1 minus. Now, we calculate the Bell-Coleman cycle equation or COP, coefficient of performance of Bell-Coleman. Heat absorbed during cycle per kg of air, that is equals to Cp T1 minus T4. We already seen previous slide. 2 4 to 1, that is Cp T1 minus T4. heat rejected during the cycle per kg of air, that is a Q223 Cp T2 minus T3. So work done per kg, that is net work, that is equals to net Q is equals to heat rejected minus heat absorbed. Heat rejected minus heat absorbed. Because in thermodynamics, the cyclic process, the cyclic integration of Q is equals to cyclic integration of W. Okay, so COP is equals to heat absorbed divided by work done. How much amount of heat absorbed? Cp T1 minus T4. Work done Cp T2 minus Cp T2 minus T3 minus Cp T1 minus T4. Put here equation and Cp cancel. Remaining T1 minus T4 divided by T2 minus T3 minus T1 minus T4. Here I take out the common T4 from numerator and denominator. From numerator T4, here T4 is a common, here T3 is a common, here T4. But we know that for isentropic process, 1 to 2 process, that is isentropic, T2 by T1 is equals to P2 minus P1 raised to gamma minus 1 divided by gamma. How it comes? We know that the PV raised to gamma is equals to constant. From this equation, we write T2 by T1 is equals to P2 minus P2 divided by P1 raised to gamma minus 1 by gamma, where gamma is equals to Cp minus Cv. For air is equals to 1.005. Air is equals to 1.00. For isentropic process 3 to 4, again written similar like T3 by T4 is equals to P3 by P4 gamma minus 1 by gamma. Since P2 equals to P3 equals to 2 to 3 constant pressure and P1 is equals to P4 because 1 to 4 is also constant pressure process. There from the above equation we write T2 by T1 is equals to T3 by T4 or T2 by T3 is equals to T1 by T4. T3 comes here and T1 goes this side. That's why we write T2 by T3 is equals to T1 by T4. Substitute this both values in COP equation. COP is equals to T4 is T4 divided by T3 minus T4 being common T4. So 1 divided by T3 minus T4, T3 divided by T4 minus 1. So we write this equation T1 by T4 by T4, T3 and T4. All other things are cancelled because we used this algorithm for these equations. T2 by T3 is equal to T1 by T4. Finally, T3 by T4, that is in terms of pressure ratio, P3 by P4, gamma minus 1 by gamma minus 1. 1 divided by P2 by P1, gamma minus 1 by gamma minus 1, because P3 by P4 is equals to P2 by P1. So finally, P2 by P1 or P3 by P4 written as RP, that is a compression or expansion ratio or pressure ratio. Finally, pressure ratio. The final COP is 1 upon Rp raised to gamma minus 1, Rp raised to gamma minus 1 divided by gamma minus 1.